All right, so today we're going to take a look at section 3.6, which is an overview of curve sketching. Our lesson itself is brief on purpose because I feel like this is one of those things that you could watch me do several of them, and that'd be great, and you could still feel like you're at a loss when you get to actually doing them yourself, so I'd rather you practice them on your own. One of the things that always frustrated my husband when he was taking calculus is that he felt like he was doing just fine in class, and then when he got to it on his own, it looked just enough different that he felt lost again. And so this is one of those sections where I think it's easy to feel that way, so we're going to do some practice before we leave. To start with, there are some different features on graphs that we're specifically going to analyze as we're working with curve sketching. Domain and range is one of those features. In particular, domain and range takes a look at, is there a square root? Is there a denominator? Are there places where I'm going to have things that I can't let x equal? Or that I actually can never let y sort of rise above if you've got a horizontal sort of a limiting feature to your graph. We're going to be looking at intercepts, so that would be x-intercepts and y-intercepts. Asymptotes, that would be horizontal and vertical. And there are slant asymptotes. I can't remember if that comes up in our stuff today or not. I think that it does not. But slant asymptotes are a third type of asymptote. And then symmetry within a graph, which is a graph symmetric with respect to the y-axis maybe. Can I flip it around the y-axis and I have the same image on both sides? And then locating values, x values, for which the derivative or the second derivative are either 0 or does not exist. And then using those results to decide, do you have relative extrema, do I have points of inflection? So issues about increasing, decreasing, concave up, concave down, all come about from the first and the second derivative. So those are the things we're going to be analyzing as we're taking a look at particular equations. Some of our equations are easier to deal with than others. So I had a student in my office the other day and we were talking about graphs in general because I think the last set of questions that you had you sort of picking a graph from among a different sets of options. Does that sound right? And so sort of identifying key features is really helpful in determining which graph is sort of the right graph from a multiple choice perspective. But from a actually graphing it perspective, you have to find those details in order to piece it all together to begin with. So we're going to take a look at that with this particular equation. All right, so we have on this one, what type of a function? Do you remember what type this is called? It's rational. Yeah, this is a rational function. I've got a ratio, and it's a ratio of polynomials, which is what makes it a rational function. Our directions say that we're going to analyze and sketch. We're going to label any intercepts, relative extrema, points of inflection, and asymptotes. So as we take a look at this, we're going to kind of go through this sort of abbreviated list. It's not super detailed because I've grouped a lot of things within each category, but we're going to try to hit on what features the graph has, and when it has those features, we're going to make sure we identify them. So domain and range is the sort of top listing item. So as you take a look at this particular equation, domain is usually easier to identify. Are there any domain issues? Anything? What do you notice, Emma?
Well, there will be vertical asymptotes because the denominator is an x value.
Right. So the first issue is that there is a domain problem at x equals 0, right? So to start with our domain is that x, and I'm going to write it it can't equal, because sometimes that's easier when we're specifically going into a graph to remember those details. X can't be 0. And I'll write down the asymptote that you mentioned here in just a minute, Emma, because we definitely do have that as well. Since the x value cannot be 0, there is going to be a problem with a y value not being able to be had as well. In particular, this is a rational function. You guys looked at horizontal asymptotes in the last section, right, when you talked about limits at infinity. So I'm going to skip down just here to put number 2 and write down what we had said about the asymptotes so far. So there is an asymptote at, what did you say, Emma?
0, 0.
That's the origin, but at x equals 0 would be the line, right? Okay, so at x equals 0, we have a horizontal asymptote. I'm sorry, a vertical asymptote, my goodness. What about a horizontal asymptote? Can you see where it would have a horizontal asymptote here? Does anybody remember from the last section, similar to the last problem in your quiz, in fact?
X equals 4.
You're thinking about intercepts. It's not at x equal 4. Horizontal asymptotes are determined by, well, one way that they're determined is by looking at the degrees of the exponents. What's the degree of the exponent on top? Or the degree of, what is the exponent? The degree of the polynomial. It's 1, right? So the degree on top is 1, the degree on bottom is 3. So when the degree on top is smaller than the degree on bottom, what does that tell you about horizontal asymptotes? Do you remember? It's equal to 0. Yeah, it's equal to 0. If the degrees were the same, we would take a ratio of the numbers in front of those highest degree terms. So like if this were x cubed minus 4 over x cubed, with the x cubes at the beginning, right, that matching right like that, then we would do 1 over 1, and our horizontal asymptote would be y equal 1. So on this one, our horizontal asymptote also is y equal to 0. All right. We'll come back to range in a little bit. It has some weird things going on with the range because, as Frankie mentioned, I do have some intercepts here to deal with. So let's take a look at intercepts next, since that was mentioned. And what you were trying to tell me about the intercepts was that there is, in fact, an intercept for the x-axis. In particular, if y is equal to 0, and we were to plug that in, so to speak, into our equation above, 0 equals x minus 4 over x cubed. Can anybody tell me what x value would make this whole right-hand side of the equation equal to 0? It's 4, right? If my numerator is 0, the whole thing's going to be 0, so the x value of 4. If you didn't readily see that, or if you didn't think through it in that way, you could cross multiply and just solve it, and you'll also get x equal 4. So I do, in fact, have an intercept when y is equal to 0, x is equal to 4. In particular, the way that we write that as an ordered pair is 4, 0. Right? What about a y-intercept? I mean, if x is equal to 0, what's going to happen? It's undefined. And so because that happens, there is no y-intercept. You don't necessarily have to write it, but sometimes it's helpful to write something down and know that you've checked it off the list of things that you actually don't have happening on your graph. So yeah, there's no y-intercept. There's actually no symmetry either, and that really shouldn't come as a surprise on this particular one, because symmetry happens a lot of times, at least the times we're going to be seeing it happen, when I have things that have even powers of exponents. Like the simplest one that you know symmetry for is y equal x squared, right? It's like this. So it's symmetric on the left-hand and the right-hand side. It happens with even powers of exponents because when I put in positive numbers and I put in negative numbers, I get the same output. And that doesn't happen when I have odd exponents, and this one only has odd exponents, so there's no symmetry either. Again, you don't necessarily have to write it down, but sometimes it's helpful to write down the things that you don't have, that you've sort of checked off the list. So the symmetry here is that there isn't any. All right, so the features that are most pertinent to calculus, everything that we've done so far is stuff we do in college algebra. There was nothing from that that's something that I really should have had to teach you, even if you haven't seen it maybe in quite a while. It's not calculus. But the stuff that is calculus has to do with derivatives. So derivatives, super fun stuff. Of course, we need to take the derivative, this is sort of step 3, if you will, of our function. So somebody help me out with the derivative of x minus 4 over x cubed. How will it begin? The bottom. So I've got x cubed, right? And then?
Minus.
Yeah, so it'd be times the derivative of the top, which is 1, and then I have a minus. Is that what you're thinking, Emma?
Yeah.
Yep. Okay, and then what did you have next?
X minus 4 times 3x squared. All divided by x to the 6th or x to the 3 times r squared.
Right. x cubed squared, which would be x to the 6. You're exactly right. So we're going to clean up what's there, but is everybody good with that part so far before I clean things up? Okay, so I have now x cubed minus 3x cubed plus 12x squared. Does that look right? All over x to the 6th. The first two pieces, of course, combine, right? So I would have negative 2x cubed plus 12x squared over x to the 6th. What else would I have? I mean, what else can I do? Yeah, everything has at least an x squared component in it, right? So I can factor out or I can reduce out, whatever phrasing you kind of like, the x squared from every term. So if I take out an x squared, this one's going to go away, this one's going to become x to the 4th, and this one's simply going to become x. So I'm going to be left with negative 2x plus 12 over x to the 4th. Part of the reason why that we simplify is simply because we can. But part of the reason that we're simplifying for like practical purposes is right now is that it's a lot easier to take the derivative of what we just ended up with right there than where we began when we took the first derivative initially. It's just a lot cleaner to work with. So we'll come back to setting this equal to 0 in a moment. I'm going to shrink some of my stuff on my screen so that I have some more space. But we're going to take the second derivative, since we're sort of in derivative mindset right now, next. So I'm just going to leave some space next to that because I am going to come back to it, but we're going to do our second derivative here. So I want the second derivative, and so I'm wanting the derivative of negative 2x plus 12 over x to the 4th. So what would that give me to start with? I'll start you out. X to the 4th. Now what?
-2.
Times negative 2.
Would it be negative?
What's that?
Would it be negative?
Yeah, negative 2 for the derivative of the top. You're right. And then I have minus. And then what?
Negative 2x plus 12 times 4x cubed.
Yes.
Divided by x to the 8th.
Okay, my type is getting kind of small. I'm sorry about that. So if I clean this up a little bit, I have negative 2x to the 4th. I have negative 8x to the 4th. And then I have negative 48x cubed. Does that look okay? And of course, all over x to the 8th. Again, kind of like the last one, these first two happen to combine. So I have negative 10x to the 4th minus 48x cubed over x to the 8th. And everything has at least n x cubed in it this time, right? So I can do what I did in the last one where I reduce everything by an x cubed factor. So the x to the 4th will become x, the x to the 8th will become x to the 5th, and of course the x cubed will simply reduce out completely. So I have negative 10x minus 48 over x to the 5th. Yes, did I make a mistake?
Well, I was just going to say, I think you forgot to break
I
up that negative.
I did.
Sorry.
No, you're fine. Sign errors are my specialty. Plus right there then, and a 6. Wow, that was not what I wanted. Let's try it again. Okay, is that better?
Yeah.
Okay. I just didn't finish it all that down here. How about that? 6x minus 48 over x to the 5th. Awesome, that actually matches what's on my paper too, so that's always good. All right. Again, we've done the calculus at this point now. The derivative, the second derivative, all the calculus is done. And now we're putting on our algebra hats again by setting things equal to 0 and figuring out what happens. So if you'll remember, our relative maxes and mins are associated with the first derivative. The first derivative, when it's equal to 0 or when it doesn't exist, has potential places. They don't have to be, but there are potential places for relative extreme values. They're maybes. So we're going to go back to our first derivative and check that out. If I take this first derivative and I set it equal to 0, when will this equal 0?
X equals 0.
Nope, that's when it's going to not exist, which we have to find in a minute. But when will it equal 0 first? At 6, right? If the numerator is 0, the whole thing's 0, and the numerator will be 0 when x is 6. So we have, what we're finding right now are our critical points. And the first one we just found was 6. The 6 happens when the numerator equals 0. But it's actually true that we would also want to figure out if there's any places where it does not exist. And it does not exist when x is equal to 0. Now, we know what happens when x is equal to 0. We have an asymptote. So there's not going to be a relative extreme value then, but there could be a place where it changes from increasing to decreasing or decreasing to increasing. So it's still a critical value. It's just not going to be a relative extrema. Okay? So let's actually figure out the increasing, decreasing part of this by using those critical points. So I have 6 and 0, written, of course, as 0 and 6, and we're testing points in and around those values. So maybe you test -1, 1, and 7. I mean, they're as good as any, right? And where do we evaluate those? Do we plug them into the original? Do we plug them in the derivative? Do we plug them in the second? Where do we use them? The first derivative. If we're doing a sign chart, we're plugging them into the first derivative. Now, I'll come back to this in just a second because there's another way to do this part of the problem. But if you're doing a sign chart, you're plugging them into the first derivative. So if I take -1 and I plug it into this simplified version of the first derivative, what will happen when I put in -1? Again, I care only about the sign. Will I get a positive or will I get a negative?
It's positive.
I will get a positive. Yes, I will. All right, what happens if I plug the number 1 in? Are you sure? It happens to be a positive on this one as well. So often our signs just alternate, and this one just doesn't happen to. But it's positive because putting in a -1 into this part or a +1 into this part is still not going to be enough to counteract the 12. But then if I put in a number that's big enough, like 7, then what will happen? Then I do get a negative. So what this is telling me is that from the left-hand side until I get to the asymptote at x equals 0, the graph is increasing, correct? And then it's increasing again after the asymptote until I get to 6. And then from 6 on, I've got a decreasing graph. So what is happening then right at 6? What is it? There's a maximum there because it goes from increasing to decreasing. So I have a max at x equals 6. Okay? All right, let me mention one other way that you could have decided. It doesn't help you decide about everything, but it could help you decide if you're only looking for maxes or mins, because there was some confusion with a couple people who've been in my office asking me about the second derivative test. You guys remember the video talking about the second derivative test? What the second derivative test says you can do is that if you have these critical numbers, 0 and 6, and you just want to find out, are they relative extrema, right? Are they maxes or are they mins? You can plug them into the second derivative, and the second derivative will tell you. If you plugged in, we know that 6 is a max now. We've already figured that out with a different test, but just so you can see it working. If I plug in the number 6, what happens? What is 6 times 6 minus 48 divided by 6 to the 5th? Is it positive or is it negative? It's negative. And a second derivative that's negative means a graph is concave down. And if a graph is concave down, that's fun. How about that one? Then it means that I have a maximum there. So that's how the second derivative test could be used. Unfortunately, the second derivative test is not telling us about increasing and decreasing, which we also need. So it doesn't give us a full picture for what we're doing right now. but it does confirm that we have that there. And if I were to try to plug in x equal to 0, you can see that the second derivative is not going to exist there, right? I'm going to get asymptote issues again, so I don't have to worry about that there. But I just wanted you to see that that's how the second derivative can be used. All right. The second derivative, however, also tells us about inflection points and concavity of the graph on whole. And so if I take the second derivative and I set it equal to 0 and equal to does not exist, I can do the same thing that I did with the first derivative by creating a number line. It's just that the number line is going to tell me issues about concavity now instead of about direction. It's not going to say increasing, decreasing. It's going to say concave up, concave down. So I need to know, where does this actually give me values? So at x equals 0, of course, it does not exist. Same thing I had just a minute ago. What happens for the other one, though? When does it actually equal 0? At 8, right? If I plugged in 8 to the numerator, I get the numerator to be 0. So I'm going to do one more number line, and then we're going to be ready to move on to the next slide where I can actually put all of this together and draw a graph. So, number line, but this number line has a 0 and an 8 on it. And I'm going to test values in between those just like last time. So again, maybe you test -1 and 1 and 10. I don't know. And you're plugging them into the second derivative. Okay, second derivative is telling me about concavity. So if I plug in -1, do I get a positive or a negative? I get a positive. What if I plug in +1? I actually get a negative, so this one did switch signs between the two of theirs. And what if I plug in 10? I get a positive. So my signs alternate on this particular chart. Okay, y'all ready to actually graph this thing now? If you want to use graphing paper when you do this, that's great. If you just want to be careful on how you're graphing, that's great too. I'm going to try and see if I've got graphing paper in here that would be useful. Try a little bit bigger grid. Maybe that one. Let's try it. Okay, so I have this going on right here. There were some features early on that were useful. It told me early on that I have some asymptotes. In particular, I'm going to do mine dotted. I had a horizontal asymptote at the x-axis, at the y-axis, and I'm saying it wrong, a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis, so I made mine dotted red. Okay? It's hard to draw those on top of pencil, but just be aware that they're there. I also had an intercept. I had an intercept at x equal 4, 0, which feels a little bit funny, doesn't it? Because that's an asymptote. It does. It feels a little bit weird. However, it's not unheard of. Asymptote has to do with what happens at the ends of the graph, right? The end behavior. So you can, in fact, cross an asymptote in the middle of a graph, and it's perfectly acceptable. Okay, asymptotes are end behavior when we're looking at horizontal asymptotes. So this is okay. As you take a look at your number line charts that we created, in particular, part of our charts match up, right? This left-hand side over here, I want to use something more solid. Over here, not so thick. And over here, both of those parts of my chart, that peach is terrible, are the same interval. They're -∞ to 0. Are you with me? What does it tell me? Well, I know it's supposed to be increasing, and I didn't write them in here, but I also know from this piece it's supposed to be concave up. So over here, I'm supposed to be on the left-hand side. I'm this, in this area of my graph. I need to be increasing, and I need to be concave up. And without anything else to go on, you should at least know that you're on the top left-hand corner of the graph, because there's no way to do what I just suggested and to be in the bottom corner. Are you with me? And you have to be getting close to the asymptotes both on the left-hand side and toward the middle. So as we're graphing this, it's going to look something like this, because it needs to be increasing from left to right, and it needs to be concave up, and these are my only ways to draw this. That's all I've got. Now, as I move toward the rest of the graph, I have these odd places where they changed places. So I've got the 4 that I marked. I've got this number 6 where something's changing, and I've got the number 8 where something's changing from the 2 different sign charts that I created. At 6, I know I'm supposed to have a relative maximum. It'd be a lot easier to graph it if I knew what the actual y value was at that particular point. So we can find that by using the original equation. So if I take my original equation and I plug in x equal to 6, what will I get? I don't have this written down on paper, so I hope that you guys can find. Oh, I do. Maybe I do. It's very small. Calculator would be helpful to calculate it. Yep. 0.009. It's almost 0, right? But it's not. It is slightly above the x-axis. So over here at 6, I need to be slightly above the x-axis. And again, this is a sketch, so I'm not looking for super-duper accuracy, but it should seem reasonable. If you put the dot below the x-axis, we're going to have problems, that kind of stuff, okay? Now, thinking about my number lines that I created over here, my sign charts, what I'm supposed to be doing before I get to 6 is I'm supposed to be increasing. And I have to cross the x-axis at 4, and I have to have a peak at 6, 0.009. So the only way, again, to connect those dots and to draw it in that way would be that my graph does something like this, right? That's what it says I have to do. All right, so what happens from 6 on according to the first derivative? From 6 on. 6 on, it is decreasing. It's supposed to be decreasing. But what happens at 8? What's that? Nope, it's not increasing at 8. There's something else happening at 8. It changes to concave up. So it's concave down from 6 to 8, right? So it's like this from 6 to 8. And then it's concave up like this afterwards. So what does that look like? What does that mean? Well, it looks something like this. From 6 to 8, 8's got to be even closer to the x-axis but not dipping beneath it. So I need to exaggerate this just to be able to draw it. Are you guys going to freak out at me if I do that? I just need an exaggeration. So it's going downward, right? And at 8, it's going to go back to leveled off so that at 8, we see a point of inflection. All right? It's concave down on this piece, and it's concave up on this piece, but it's not actually increasing again. It's just leveling off, but concave up. Because the numbers are so small, it's difficult to draw it well, but that's what we have going on. Notice we're also leveling back off. We're not crossing the x-axis. Again, we know we don't cross the x-axis, again, because there were no more x-intercepts, right? Only had one. And it's an asymptote, so I have to be getting close to it as well. Kind of hugging it. In terms of kind of finishing things up, I'll draw some arrows on the ends of things, and we're good to go. All of the work that we did over here is what supports the fact that the graph has to seem like it looks like this, has this shape, these features. All right. Now, here's the reality. I think it took us about 25 minutes, and of course, I went slowly because I had a lot to explain. So if you did this problem and you knew what you were doing, it wouldn't take you 25 minutes to do this problem. But even if it took you 15 minutes to do this problem, that's a long time for one problem on a test, right? So there are problems that will take this long. They may not show up on a test because I only have so much time to test you on, and you got lots of material, right? There are other problems that are simpler to work with, but you still are finding the same features. I could give you a polynomial. You know what a basic x-cubed polynomial looks like. It looks something like this, right? But I could ask you to do all the same things. You have to find the derivative, you have to find the second derivative, you have to set them equals to 0, you have to find these sign charts. All the details are the same. It's just easier to work with because the derivatives are easier to work with. Are you with me? Okay, so let me take a look at another one with you. Same kind of instructions. And we're doing the same thing, but it's a different type of function. What kind of a function is this one? Not a polynomial, and it's not rational. It's not a trick question either.
Graph.
It's a radical function. Yeah, it's a radical function. And there are, in fact, domain issues with radical functions, right? You betcha. So what do you know about radical functions and domain issues? Remember? What things can you and can you not have when you're dealing with radicals, square roots in particular?
Have negative.
Where?
Inside of the.
You can't have a negative value
The whole
overall.
thing you can't have a negative number inside of the square root.
Right, so like this negative one's okay, right, Emma?
Yeah, but the whole
Okay,
thing.
right, so this whole thing needs to be positive, yeah? So what I really need is I need 2x minus 1 to be greater than or equal to 0. Okay, 0 is fine. Everybody good with that, right? Like the square root of 0 is 0. So it's okay to equal 0, but it's not okay to be negative underneath a radical, not when we're working with real numbers. And if I solve this, this tells me that x value has to be greater than or equal to 1/2. So in terms of a graph, when I draw it over here, let me clear this screen. And I will make my graph have a bigger grid this time. I know that my graph, and this is, I'm going to do this one in a different order. The last one we found out all the information before we started putting things on the graph. On this one, I think I'm going to try to do all the graph at the same time that I do the others. So let's try that one on this one. That's what I want. With a thinner line. Okay. So if this is my graph, then 1/2 right here. And I need to be on the right-hand side of it, okay? And in particular, if I actually have the x value of 1/2, right, what is f of 1/2? It's 0, right? If I plug in 1/2, I get 0 underneath the square root of 0 is 0. So that's actually an intercept as well. So I actually have an intercept right here. So over here, when I'm finding all these pieces, my intercept, there's not a y-intercept because I can't get that far over there. 1/2 is where I have to stop, right? I can't get to 0 on the y-axis or on the x-axis. But I have an x-intercept at 1/2, 0. We didn't deal with the range on the last one because it was not super helpful to deal with. But it probably would be helpful to deal with it at least a little bit on this one. As I'm looking at this particular range, because I'm dealing with a square root function, remember range are output values. So when you have a square root, what kinds of values come out of a square root? Only positives. These are principal square roots. We don't put plus or minus on things when the square root's given because it's asking you for the principal square root. So my range is actually 0 to infinity. Or you could say y is greater than or equal to 0. I'm strictly going to be above the x-axis as well. Okay, everybody good with that? Above the x-axis. Now, the chances are you know probably what this graph roughly looks like. Yes, Eric?
Shouldn't there be a bracket around the infinity and not on top of the bracket?
There should be a parenthesis around the infinity, yes. Because we don't equal it. Thank you. We can equal 0 for a y value, but equaling infinity is it's not a number, it's a concept. All right. So we have our domain, we had our range, we had our intercepts. There's no asymptotes because I don't have any denominators, right? So asymptotes don't exist. Again, symmetry, I can't even get to the other side, so to speak, of either of the axes, the x-axis or the y-axis, so there's no symmetry. And again, if you simply don't write those down, it's okay, but just to be aware that we've sort of thought through that. All right, so the calculus part was to take derivatives, right? So let's take the derivative of this one. And it might be helpful if you think about it being written how instead. Right, to the power of 1/2. So I have 2x minus 1 to the 1/2. What would the derivative of that be? 1/2. Now what? 2x minus 1 to the negative 1/2. And then I need to multiply by 2 for the inside. This one's actually kind of nice because the 1/2, the 2 are going to cancel out. That doesn't always happen, of course. But I end up getting 1 over the square root of 2x minus 1. For the purposes of the second derivative, let's keep moving, and then we'll come back to setting this equal to 0. I'm just going to skip a little space here. If I do the second derivative, it's easier to do the second derivative from here, right? With the negative 1/2 going on. So if I do the second derivative, what do I get?
I guess it's just 1 over radical 2x minus 1.
Well, we bring the negative 1/2 down, so negative 1/2, right?
Yeah.
And then what would my new exponent be?
2x minus 1 to the negative.
Yeah, negative 3/2, yep. And then again, I'd have times 2. So the 2 is going to cancel with the 2 in front again in the denominator like that, but there's a negative on this one. So if I simplify and write this one differently, I actually have negative 1, or a negative in front if you prefer, over the square root of 2x minus 1 cubed. You could put the cubed inside the radical or outside the radical, doesn't matter, but it applies to everything under the radical. The reality is that both of those are quite similar, so when I set this equal to 0 or equal to does not exist, they're going to be the same locations because these two ending results are quite similar, right? They're going to have the same features. So this is equal to 0 or does not exist. So somebody tell me what happens when I set these equal to 0. Where do these equal 0? Nowhere. That's exactly right. Because it's got to be the numerator that equals 0 for a fraction equals 0, and the numerators are 1. There's no way for that to happen. So this is just not an option. It can't equal 0. Where is it going to be equal to does not exist? I already solved it before. Yeah, 1/2, right? 1/2 is going to be the problem. So anything less than 1/2, it's not going to exist for either. Well, like if you think about my graph here, kind of already knew that, right? Like nothing's happening before 1/2. So what does that tell me is happening aside from that? Well, it tells me that I only have really one area of a graph to test. The only area I really have to care about is what happens after 1/2. And so I can test any number after 1/2. I kind of like the number 1. The number 1 is usually a very friendly number to test. And the same thing over here. If I'm testing this for concavity issues, I can still test the number 1. So if I plug the number 1 into the equation up here, do I get a positive or a negative for the whole thing overall? I'm going to get a positive, right? I'm going to get a positive from the denominator automatically because there's a square root of something that gives me positives. And the numerator is also positive, so this is going to give me a positive, which tells me that the graph is going to be increasing everywhere after 1/2. It's an increasing graph only. What happens when I put the number 1 into the second derivative? No, it doesn't give me 0. I'm not plugging in 1/2, I'm plugging in the number 1. Do I get a positive or a negative on this one? It's negative. Because again, the denominator has to be positive because it's the radical, right? Yes? And I got a negative in the numerator on this one. So this is negative. So what does that tell me about this graph's second derivative? What does the second derivative tell me about this graph? It's concave down. So it's concave down everywhere, and it's increasing. What does that look like? Well, it looks like this. That is concave down and increasing. And that's what we would have. The fact that it never equaled 0 up here also tells us that there's no relative extrema. Right? Yeah, there's no relative extrema happening on the graph. Any questions on that? All right, so what I'd like for you to do, remember you're going to have written work, is that you have 4 problems, 16, 23, 28, and 31. I'd like for you to snag somebody in the classroom, or 2 somebodies, no more than 3 per group, please, and take a look at least one of those 4 problems and accomplish it before you leave. If you can get to more, then that's fantastic. But try to get through at least one of those so that if you run into a problem, I can help you before you head out of the classroom, okay?